This is section 9.6, solving nonlinear systems of equations. Ultimately, you have solved systems of equations before, but they are always linear. You were looking for the intersection point of two lines. In this section, you could have two graphs where one's a line, but one is not, and that's what makes it into a nonlinear system. So let's say one's a parabola, and the other one is a line of some sort. Then you'd have a potential for two intersections. Or let's say you've got a circle and a parabola, well then you've got the potential for four intersections. So there are multiple possibilities when you have a nonlinear system. It's no longer one solution. If the lines are parallel, no solutions, or if they intersect right on top of each other at every single point, then infinitely many solutions. But now you've got more possibilities. So one thing that this could be applied to in real life is, I actually have this video right here, the attempted world record car jump. Now, they've got right here on this video, it says final jump target speed 160 kilometers per hour. The way that they were able to come up with that is by solving a system of equations based on the distance between the ramps, the weight of the car, the gravity pulling on the car, and all of that. Now, unfortunately, they forgot about one little thing, but let's watch this video for a second here. So I don't know exactly how that looked with my recording software here, but I'll watch this back later. Hopefully it looked okay to you guys. But ultimately they forgot about the rotation that the car would go through while it was in the air, and it rotated down way too quickly, and he ended up landing almost perpendicular with the ramp. He was fine, don't worry. But anyway, so what they ultimately did there was solve a system of equations. Like I said here, the parabola is the car's trajectory after it launches off the ramp, and then you can use a line from one ramp to the height of the other ramp, and then you can figure out the speed that you'd have to go in order to make that jump. And obviously you don't just want to just hit the gas and hope for the best, because if he shorts that jump, he's going to crash right into the side of the ramp, and that would be much worse than crashing on top of the ramp. All right, so let's get to it. In this one, solving these nonlinear equations, a system of nonlinear equation. Again, a system of nonlinear equations just means at least one of the equations is nonlinear. So you could have one that's a line and one that's not. They could both be nonlinear, like a circle and a parabola, but you just can no longer have a system with both of the equations being lines, or all of the equations being lines, because that's a linear system of equations. And today we're solving nonlinear systems of equations. All right, so how many solutions could you have? Well, you could have one solution if they intersect at one point. You could have two solutions to the system if they intersect at 2 points, or no solutions to the system if they intersect at no points. As I mentioned before, you could have more than that. In Algebra 2, you are going to have somewhere you have like a parabola and a circle or an oval, and it could intersect at 4 points, and you could have other graphs that intersect at more points. But in Algebra 1, we are only going to have either 1, 2, or no solutions, so just keep an eye out for those three options. But ultimately, the solutions to the system of nonlinear, the solutions to the nonlinear systems are the intersection points if you were to graph them. So keep that in the back of your mind. You can have 1, 2, or 0 solutions because we're trying to find the intersection points, and on all of these, we're going to be dealing with only 3 possibilities. Now I might give you one that is a circle and a parabola, but again, I'm going to keep it to 2 solutions or fewer. All right. So on this one, I'm showing you on every single example we're going to get into today, which there are 3 examples. I'm going to be showing you what it looks like graphically. So you already know what the solution should be. This is a solution, one of the intersection points, and this is another solution. We know what we should get. I'm just showing this to you so that you can see visually what this is looking like as we solve it algebraically. So the directions say solve by using substitution, and we should be able to get these solutions algebraically using the method of substitution. All right, so this is a system. Let me show that using my set bracket here. And solving using substitution, remember to substitute means to plug in for something else. So this says that y is equal to this expression x squared plus x minus 1. It's the same as this expression. Y is the same as this expression. So instead of writing a y here, if y is the same as this expression, I can substitute this in for y, replace y with this expression. So this equation will become, instead of y equals, it will become this expression because it's equal to y. X squared plus x minus 1 equals, so I just replaced y, I substituted this in for y, and that's what that becomes. It still equals negative 2x plus 3. So that's using substitution. That very first step, that's where I'm using substitution. Now I need to solve this equation. I need to solve a quadratic equation, and you've got different methods to solve this. You've learned 4 different methods. You could solve using completing the square, factoring if it's factorable, square roots if it's in the form ax squared plus c equals 0, or solve by using the quadratic formula. You've got 4 different methods. So all 4 methods require that you have it set equal to 0. So I'm going to add 2x to both sides, and I'm going to subtract 3 from both sides, and my equation becomes x squared. If I add 2x to both sides, this is plus 3x, and if I subtract 3 from both sides, this becomes negative 4, and that equals 0. So the fastest method, in my opinion, is factoring, if it's factorable. So can I factor this? Well, let's figure this out real quick. If I try to factor, these two are going to have to multiply to be a negative 4, something in 4 and 1. I need a positive 3x, so positive 4 and negative 1. So I can factor this very quickly. You could use a quadratic formula, but then you're going to have to write out that whole formula, simplify, get your answers. You could use completing the square, but on this one, that middle coefficient's an odd number, so I wouldn't want to use completing the square, because then I'd have to add half of 3 squared to both sides, and that would get messy. So in my opinion, if you can factor it, factor it. Then use the zero product property, where if you multiply 2 factors and get out a 0, one of them must equal 0. X plus 4 equals 0, or x minus 1 is 0. So we get x equals negative 4, or x equals positive 1. Now, this is a little bit different than what we've been doing in the past. We're not just looking for the x coordinates. So in the past, we had one equation that was set equal to 0, and we solved this and got our answers. Well, yes, these are the answers to this equation, but I'm trying to find the intersection points. Solving the system means find the intersection points between those. So I'm not done. I need to plug these back in and solve for y. Let me make a note of that on here. Plug these values in for x and solve for y. And I should really be using correct math terminology. Instead of saying plug them in, I should say substitute these values in for x and solve for y. I'm starting to lose my voice. Substitute these values back in for x and solve for y. All right, so you can use either equation to substitute them back in for x. You will get the same value, but choose the one that looks easier. So I think the linear equation looks easier compared to the quadratic equation. There's fewer places I have to plug it in. I don't have to square anything, so I'm going to use the linear equation here. So I'm going to say, for one of these, y equals negative 2, x is now going to be a negative 4 plus 3. So for this first value of x, I get positive 8 plus 3, which is 11. So one solution, one intersection point, when x is negative 4, y is 11. That's one solution. For the other solution, I need to plug this value of x in for x in my equation. I'm going to again use the linear equation, so negative 2 times x is 1 plus 3. So that becomes negative 2 plus 3, which is positive 1. So on that one, I get when x is 1, y is 1. And you can see here, negative 4, 11 and 1, 1 are the two intersection points that you can see graphically, but we wanted to solve this algebraically using substitution. Again, this is just a visual so you can see what's going on, but those are my solutions. And here's how we represent these using set notation. So up to this point, you had just values that were your solutions, -4, 1, so we'd put those in a set bracket. But now we have points that are our solutions. So here's how we write it. We say the set of, what are we dealing with here? It's not just x or y, it's the set of points that are in the xy coordinate plane. So we say the set of xy such that, and then we list out all of our solutions, all of our intersection points. My intersection points are 1, 1, and -4, 11. I suppose -4 is smaller than 1. I'm going to put that one first. -4, 11, and 1, 1. And that's it. Those are my solutions. All right, so we just have 2 more examples to go. This one says solve using elimination. So to eliminate, what we do is either add or subtract. Now, technically, the method elimination used to actually also be called elimination or solving by subtraction. So we should be subtracting. I realized as I was saying that I was saying it wrong. I'm sorry, it's elimination or addition. Elimination used to be called the method of addition. So to solve this, I could try to add these together right away, but then x's and y's would still exist in my equation. So that's not going to eliminate one of my variables. So what I'm going to do to start is multiply one of these equations by -1 on both sides. If I do that and distribute the -1 over here, this turns into y equals x squared minus 3x minus 2. The bottom equation turns into a -y equals positive 3x plus 8. And then if I add these equations together, y plus -y is 0. I eliminate the y's. X squared plus, well, I have no other like terms in the other equation. I have no other x squareds down here, so x squared plus nothing is x squared. -3x plus positive 3x is 0, so I don't have a middle linear term. And -2 plus 8 is positive 6. All right, so on this one, notice on the graph there's no intersection points. I know I'm going to have no solutions, but how do I show that over here? I could solve using quadratic equation, but this one is in the form 0 equals ax squared plus c. There is no linear term, no bx term. So I'm going to solve using square roots. Subtract 6 from both sides, you get -6 equals x squared. Try to take a square root to undo that square, but here's what happens. You get the square root of a negative number. We're not going to be able to have a value of the square root of -6 in the real number system. So there are no real solutions. And graphically, again, that means that those graphs do not intersect in the xy coordinate plane. There is no intersection, so that's why we have no real solutions. All right, last example, moving on here. Solve the system of equations. It doesn't say it doesn't say elimination or substitution. You get to pick. So we know that there's supposed to be a solution here, 0, 1. You can see it graphically. I mean, when you're doing your assignment, you could technically plug these into graphing software just to know what you're supposed to get. Or if you want to do it after the fact to double check yourself, that'd be good too. But what I'm going to look at here is, should I use elimination or should I use substitution? Well, if I want to use substitution, I would have to solve for a variable first in order to substitute it into the other equation. I don't want to have to do that, because if I use substitution, if I use elimination, I already have an x squared and an x squared. There's no other x's in here. I can eliminate those x squareds. So just like the last example, I'm going to start by multiplying one of these equations by -1 on both sides. Multiply by -1. My system becomes x squared plus y squared is 1. In the bottom equation, distribute the -1, we get -x squared plus y is negative times a negative is positive. If I add these together, I get x squared plus -x squared is 0. It eliminates the x squareds. Y squared plus y is y squared plus y. Those are not like terms, so you can't combine them. And 1 plus 1 is 2. Well, I can solve this equation, get it set equal to 0 by subtracting 2 from both sides. I'm going to try to solve by factoring. Let's see, I need them to multiply to a -2, so I'm thinking positive 2 and -1. So y squared minus y plus 2y is positive y minus 2. Yep. All right, solve using the zero product property. So one of those factors must equal 0 for the product to equal 0. Solve these, you get y equals -2 or y equals 1. And you might be going, well, wait a second, why do we have two y coordinates if there's only one solution? Well, keep going with this for a second. Let's see what happens. So if I plug these in, I can choose either equation. The second one, in my opinion, looks a little bit easier, so I'm going to use the second one. I have x squared minus y equals -1. Y is -2, so be careful. I didn't solve for x, I solved for y. Y is -2, so I'm going to plug that in for y. X squared minus y is -2. The double negative makes a positive. Subtract 2 from the other side here, we get -3. Try to take the square root of both sides and we get the square root of a negative. So this one gives me no real solution. No real solutions. So when I try to plug in -2, I don't get a real solution. That's why this is not going to show up on my graph. I don't have a y-coordinate of -2. Only the y-coordinate of 1 gives me a real solution. So I can show that one as well. So on the next one, I shouldn't have put a cross through there. Y does equal -2, but there is no x-coordinate in the real number system that shows an intersection. All right, so then on the next one, if y is 1, x squared minus y equals -1. I'm going to use that second equation again. Plug in 1 for y, I get x squared minus 1 is -1. Add 1 to the other side, I get x squared equals 0. Take the square root of both sides, and I get the absolute value of x equals, wrong color there. The absolute value of x equals, the square root of 0 is 0, so x equals plus or minus 0, which both of those just gives me a 0. So x is 0 when y is 1. 0, 1. So I can still use set notation, the set of x, y, such that, and then list out my solutions. In this case, just one of them. 0, 1 is my only solution, and that is what you can see graphically right here. That's where they intersect. So again, you can solve. If this were to say no solutions for this one right away, that would tell me that I'd only have one potential solution. But on this one, we got two potential solutions when we solve for y. But when plugging in one of those for y into one of my equations, I got no real solutions there. Plugging in the other one, I did get a real solution, so that's why there was only one intersection point. All right, your homework here is a book assignment. I am going to open it up and I'll go through some of these with you. Let's see. I'll go through the evens with you. You will be responsible for the whole assignment. You can copy down my work for the evens or try them and then compare your work to my work. Let me get that open real quick here. All right, here is your assignment. So again, I'll go through the even problems with you. So starting with number 4. On number 4 here, it says match the system of equations with its graph and then solve the system. Well, match the system with its graph. If you look at these linear equations, y equals x plus 1, y equals -x minus 3, this one's y equals x minus 1, and this one y equals -x plus 3, they all have different y-intercepts. So if you look at the graphs on here, just look at the lines and look for their y-intercepts, and that will tell you which one of these the graph matches with. It's that simple. You just look for little hints like that. So on number 4, I'm looking for the graph with a 0, -3 y-intercept for the line graph. Well, 0, -3, right here, 0, -3, that's this one. So D must match up with number 4. But the directions say solve the system. Well, you can look graphically and use this as your aid to solve. So you can see the solutions where they intersect. So on part D here, there's no intersection, so there are no real solutions. It's that easy. All right, you have to do number 5, but number 6, look at the one, the graph with a 0, 3 y-intercept, and that's got to be C. So 6 is C. Looking at the intersections, we've got negative 2, 5. So my solutions, the set of x, y, and my solutions are negative 2, 5. That's one of them. And then 1, 2 is the other one, the other intersection point. So that's it. That's all you have to do for your other two problems, 3 and 5. All right, moving on to the next set, 13 through 15. I'm going to go through number 14 with you. Find them over here. It says solve the system by substitution. So on number 14, the system is y equals negative 3x squared and y equals 6x plus 3. So we've got a parabola, this quadratic equation, and a line, this linear equation. So again, I'm thinking I could have no solutions, one solution, or two solutions, depending on what the graphs look like. All right, so I'm going to solve this one using, what do I feel like using? I'm going to use substitution. Oh, I'm sorry, no, it says in the directions we have to use substitution, so that makes that choice easy. All right, I'm going to take this and substitute it in for y, since y equals that expression. So this equation becomes negative 3x squared equals 6x plus 3. So to substitute in this expression for y because it equals y. To solve this, I need to get it equal to 0. So add 3x squared to both sides. Now I can see my a, b, and c coefficients. So I again want to try to factor just because that's the fastest way I can do this. So I'm going to take out the greatest common factor, since there is one that exists on this one, it's 3. After I remove that greatest common factor, this is what's left. I'm going to try to factor this trinomial. They're all addition symbols, so I have two addition symbols in my factors. I need to multiply these last two, need to multiply to a 1. Well, 1 and 1 are my only options. So x squared plus 1x plus 1x is 2x plus 1. Yep, that's the factored form. To solve this, if you're multiplying three factors together and getting out a 0, one of them must equal 0. Well, 3 can never equal a 0. And then these are the same thing, so I don't need to set each one of those equal to 0 and solve. I'd get the same value. So I just need to set one of those x plus 1s equal to 0 and solve. And I get x equals negative 1. But again, that's not my final overall answer, x equals negative 1, because I have x's and y's in my system. So I need to plug that back in, substitute that back in for x into one of these equations. So I'm going to use the linear equation, y equals 6x plus 3. If I substitute that in for x, I get y equals 6 times negative 1 plus 3. So I get y equals negative 6 plus 3, or y equals negative 3. So my solution here, the set of x, y, those are my intersection points. My only intersection on this one is negative 1, negative 3, and that's my answer. All right, moving on. The next one that I will do, the last one that I'll do, is 24. I'm only doing the even problems, so 24 coming up. 24. All right, so on this set of problems, you have to do 23 through 25, so you have to use elimination, and then 57 we can talk about briefly, but 24, let's see what it says here. 24 is the solution, or the system. We've got a quadratic equation, a parabola, and another linear equation, a line. So 24, we've got y equals x squared plus x plus 1, and the other equation, y equals negative x minus 2. We have to use elimination. So on this one, again, just like on the examples, I'm going to multiply both sides by negative 1. So that one of these y is positive, the other one's negative. Multiply by negative 1. Distribute here. The system turns into, and the first equation doesn't change, but the second equation becomes negative y equals positive x plus 2, because when you multiply by that negative, both of these are going to flip their signs to positives. Now that I've got the opposite signs here, I can add these together. That's going to eliminate the y's. I get out a 0. Y plus negative y is 0. X squared plus, there's no other x squared terms down here, so it's just x squared plus nothing is x squared. X plus x is 2x, positive 2x plus 2x. and 1 plus 2 is 3, so positive 3 plus 3. Now I need to try to solve this. I'm going to try to solve using factoring. Those are both plus signs, so 2 plus signs in my factors. They need to multiply to get 3. I'm thinking 3 and 1. Well, if I double check this, I'd get x squared plus x plus 3x. That's 4x, but I need a 2x, so that's not going to happen. I'm not going to be able to factor. So I'm going to use quadratic formula. All right, x equals negative b plus or minus the square root of b squared minus 4 times a times c, all over 2a, 2 times 1. So that becomes negative 2 plus or minus the square root of 4 minus 12. 4 minus 12. 4 minus 12 is a negative 8. So that's why I couldn't factor this one, because my solutions are actually not real solutions. There are no real solutions because I'm trying to take a square root of a negative number. So this tells me that there are no real solutions. There are no intersections. And again, if you're not confident with that, you could always go on to, I use desmos.com, desmos.com, and you can just plug in your system. You can graph both of these, so y equals x squared plus x plus 1, and the other one y equals negative x minus 2. And you can see that there are no solutions, there are no intersection points. All right, so that was the last even one, but I do want to talk briefly about the last question, number 57, that you will have to do on your own. 57, and there she is. All right, so this one says a system of equations consists of a quadratic equation whose graph opens up. Well, and then also a quadratic equation whose graph opens down. Remember, quadratic equations are always parabolas. So on 57, you've got a parabola that opens up and a parabola that opens down. It says describe the possible number of solutions of the system and sketch all the examples to justify your answers. So if you have two parabolas, you could have them look like this, you could have them look like that, you could have them look like this. So remember, the solutions are the intersection points, and that's all I'm going to say about that. Hopefully that was enough for you to understand how to go about showing the work for 57. All right, if you have any other questions, let me know. Send me an email, send me a text, do what you got to do. Have a great day.